Let's talk about the remainder estimate for the integral test. Now, we know that we can estimate the sum of a series by using a partial sum. In other words, if I had some infinite series like the infinite sum as n goes from 1 to infinity of an. Now, if you'll allow me, let me change that n to i's because I want to really split this infinite sum into a partial sum, which would be as I goes from 1 to n of the ai, plus some infinite tail. So the infinite tail would go from I goes from n plus 1 to infinity of ai, like that. So this first part right here, this part is my Sn, and that's the nth partial sum. And this part right here is what I call the infinite tail. Infinite tail. Okay. Now, an estimate isn't really useful unless we know how bad the error can be. Can be. In other words, what we want to do is we want to bound the infinite tail. This second piece right here. In other words, the first piece is our estimate. If I know how bad, or if I can bound this infinite tail over here, then that tells me how bad the error can be, because this sort of infinite tail represents the amount of error that we have. Okay, so let's take a look at a couple of pictures. If we look at this picture on the left side over here, and these boxes represent the infinite tail. So maybe I should label that over here. These boxes here, this represents the infinite tail. Okay. And then we try to approximate that error by calculating an integral. So let's say we have this, let's just shade it in blue. This blue area right here, this represents the area of the integral. So maybe I'll label that as this is integral. Then I think what we can see is that this integral represents an overestimate of the error. So the integral going from really n to infinity, f of x dx, this represents an overestimate of the error. Okay. Similarly, if you look at the picture on the right side over here, again, we have these boxes. These boxes represent the infinite tail. So just I'll relabel these guys. This is the infinite tail. Okay, and when I calculate the area under the curve, let me shade that in blue again. This area under the curve, you can see this time the area lies below the boxes. So really, this integral from n plus 1 to infinity of f of x dx, this represents an underestimate estimate. Okay, so we can really bound the amount of error by calculating two integrals. One integral that starts at n and the other integral that starts at n plus 1. So these ideas are what we mean when we talk about the remainder estimate for the integral test. So I want to remind you that we have some conditions for running the integral test. The conditions were we needed our series to agree with a function, and that function needed to be continuous, it needed to be positive, and it needed to be decreasing, okay, for all values of x beyond some number n. And in order for us to really talk about approximating a series, we really needed that our series had to be convergent. So if that was the case, then, and we could approximate it, then we can describe the remainder to be exactly the sum of the series minus the partial sum. In other words, I'm saying this whole series sums to s, like that. And we can really bound this remainder term. So just to be perfectly clear, this remainder term is what I was calling the infinite tail that was described up above, okay? And this is the remainder term of the nth partial sum. So we can bound that error as follows. The remainder is going to be in the middle. The upper bound is going to be what our overestimate was, which went from n to infinity, f of x dx. And the lower bound is going to be our underestimate, which was the integral from n plus 1 to infinity, f of x dx. Okay, so this concludes our video about the remainder estimate for the integral test. We'll work out some examples in class together. Take care, everyone.